Hey there, science fans! Today we're diving into something truly amazing, metamaterials. Now, what are they? Imagine building with Lego bricks, but on a microscopic scale. Instead of using natural materials like wood or metal as they are, we design tiny, artificial structures. These structures are smaller than the wavelength of light or sound. They are arranged in repeating patterns. This lets us give the material brand new properties that you just can't find in nature. It's like we're rewriting the rule book for physics. We're telling waves exactly how to behave. It's engineering on a whole new level, and it's incredibly cool. So we have these special materials, but let's add a twist. Let's make them. What does that mean? Well, in a regular or linear material, the output is directly proportional to the input. If you shine a little light on it, you get a little effect. If you shine twice as much light, you get twice the effect. It's predictable. But nonlinear materials don't play by those simple rules. When the light gets intense enough, they start to do strange and wonderful things. Their properties change depending on the strength of the wave hitting them. Think of it like a speaker that sounds normal at low volume, but starts to distort in interesting ways when you turn it way up. This nonlinearity is the secret sauce. It's what makes metamaterials so powerful and futuristic. When we combine the custom-built structure of metamaterials with this nonlinear behavior, we unlock a world of possibilities. It's like giving our Lego creation a superpower. Suddenly, it can react to its environment. It can change its function on the fly. A nonlinear metamaterial isn't just a passive block of stuff. It becomes an active, dynamic system. It can manipulate energy in ways we once only dreamed of. This is where science fiction starts to become science fact. We are building materials that think, in a way. So, why should you care about all this? Because these materials are not just a laboratory curiosity. They are the building blocks for the next generation of technology. We're talking about devices that are smarter, faster, and more efficient than anything we have today. By controlling how these materials interact with light, sound, or heat, we can design revolutionary new tools. From invisibility cloaks, yes, really, to computers that run on light, the potential is mind-boggling. These tiny engineered structures are poised to change everything, from medical imaging to how we power our homes. So stick around because things are about to get really interesting. Let's talk about light. Light usually travels in a straight line. When it hits a material like glass or water, it bends. We call this refraction. It's why a straw in a glass of water looks broken. Metamaterials take this to a whole new level. Because we design their structure, we can make light bend in ways that are impossible for natural materials. We can bend it backward, for example. This is called negative refraction. It's like throwing a ball into a pool, and instead of slowing down and sinking, it curves back toward you. This incredible control over light is the key to many of the amazing applications we're going to explore. Now let's bring back that nonlinearity. With nonlinear metamaterials, the bending of light depends on its intensity. A weak beam of light might pass straight through, but a strong laser beam might be bent at a sharp angle or even focused down to a tiny point. This is like having a smart lens that changes its focus automatically based on how bright the scene is. This dynamic control is a game changer for optics. We can create switches that are flipped not by electricity, but by a pulse of light. Imagine data traveling at the speed of light, being routed and processed without ever slowing down for electronics. This ability to manipulate light leads to some fantastic new devices. One of the most exciting is the superlens. Regular lenses are limited by something called the diffraction limit. It's a fundamental rule of physics that says you can't focus light to a spot smaller than about half its wavelength. This is why we can't see atoms with a normal microscope. But superlenses, made from metamaterials, can break this rule. They can capture the fine, detailed information in light waves that is usually lost, allowing us to see incredibly small things. We could image viruses in action or spot tiny defects in microchips. Another amazing trick is changing the color of light. This is called frequency conversion. In a nonlinear metamaterial, you can send in light of one color, say red, and get light of another color, like blue, coming out. Or you could combine two beams of infrared light, which is invisible to our eyes, and generate a beam of visible green light. This is incredibly useful. It could lead to more efficient lasers for medicine, better displays for our screens, and even new ways to detect harmful chemicals. We are no longer just guiding light, we are transforming it. It's like being a wizard of the electromagnetic spectrum. So, what can we actually build with these incredible materials? Let's start with those super lenses. Imagine a doctor being able to see individual proteins inside a living cell, watching how a disease develops in real time. That's the promise of super-resolution imaging. By using metamaterial lenses, microscopes could become powerful enough to break past old limits, giving us a front-row seat to the microscopic world. This wouldn't just be for biology. Engineers could inspect computer chips for flaws that are currently impossible to see, leading to more powerful and reliable electronics for everyone. It's a revolution in how we see the small stuff. But it's not just about light. Nonlinear metamaterials are also fantastic at managing other kinds of energy, like vibrations or heat. Think about all the wasted energy around us. The vibrations from a passing train, the heat from your laptop, or the radio waves filling the air. What if we could capture that energy and use it? That's energy harvesting. We can design metamaterials that absorb these ambient vibrations or temperature differences and convert them into useful electricity. Imagine a sensor on a remote bridge that powers itself just from the vibrations of traffic. No batteries needed, ever. Let's talk about protection. Sensitive electronic equipment can be easily damaged by strong electromagnetic pulses, whether from a solar flare or a nearby power surge. Metamaterials can act like a smart shield. We can create sheets of this material that are transparent to normal signals, like your Wi-Fi or cell service. But if a dangerously strong energy pulse comes along, the material's nonlinear properties kick in. It instantly changes to block or absorb that harmful energy, protecting the delicate electronics inside. It's like having a bodyguard for your gadgets that only shows up when there's trouble. And the applications keep coming. Think about wireless power. Charging your phone by just placing it on a table is already pretty cool. But with metamaterials, we could make it much more efficient and enable it to work over longer distances. We could create surfaces that focus radio waves directly onto your device, charging it quickly without wasting energy. Or consider holograms. Nonlinear metamaterials could lead to dynamic, high-resolution holographic displays that feel truly three-dimensional, changing the way we interact with information and entertainment. These aren't just small improvements, they are giant leaps forward. As we look to the future, it's clear that nonlinear metamaterials will be at the heart of making our technology smarter. We're moving away from devices that just follow simple commands to ones that can sense, adapt, and react to their surroundings. A metamaterial-based device isn't just a static object, it's a dynamic system. Its properties can be tuned in real time by light, heat, or an electric field. This opens the door for smart windows that adjust their tint to block glare, antennas that can change their own shape to find the best signal, and even materials that can repair themselves when damaged. One of the biggest trends in technology is miniaturization. We always want things to be smaller, lighter, and more portable. Metamaterials are perfect for this. Because their amazing properties come from their structure, not their bulk, we can achieve incredible functionality in a very thin layer. An entire complex optical system with lenses, filters, and switches could be flattened down into a single paper-thin sheet. This means smaller cameras for our phones with better zoom, more compact medical diagnostic tools, and lighter satellites that are cheaper to launch into space. We can pack more power into smaller packages. This all adds up to a more powerful and efficient world. Consider solar power. Metamaterials could be used to trap and concentrate sunlight, making solar panels much more efficient at converting light into electricity, even on cloudy days. In computing, using light instead of electricity to process information, a field called photonics, could lead to computers that are thousands of times faster and use far less energy. From more efficient wireless communication to sharper medical imaging, the impact of these materials will be felt across almost every field of science and engineering. We're talking about a fundamental upgrade to our technological toolkit. So the next time you hear the term nonlinear metamaterials, don't be intimidated. Just think of it as us learning to build with smarter bricks. We are creating materials that do exactly what we want them to do, manipulating waves and energy with unprecedented precision. This journey of discovery is paving the way for a future that is more connected, more efficient, and more amazing than we can even imagine. From tiny self-powered sensors to grand city-sized communication networks, these materials are unlocking a new reality. And that, my friends, is what science is all about. Consider it.